Well, today is Monday, November the 9th. This is Mr. Hobbs AP Chemistry class. If you're enjoying these videos, please feel free to subscribe to my channel. Okay? Trying to get to 100, y'all. Trying to get to 100.
I think you passed 100.
Have I? Last time I looked at it, 67. Yeah, worldwide thing. There we go. All right. Today we want to tie up some loose ends just about covalent bonding. Okay. There is a special scenario that occurs sometimes, and with one of the ones that we actually did. Well, I don't want to say that. So when we look at bonding, sometimes when we have double bonds, sometimes we have more than one possibility. So this is going to be entitled resonance. Okay, resonance. If I look at the sulfur trioxide, SO3, it has 6 to 18, has 24 electrons. So I go oxygen, oxygen, oxygen. And I have my 24 electrons. But what is the essential atom is electron deficient, right? So what do I need to do? Make a double bond. But I got a choice, right? All three of these are equal. So I could have done this. Or I equally well could have done it this way. And notice that because I have the double bond, it's like an AX3, I do a trigonal planar around this versus the tetrahedral kind of around that. That's kind of why the electrons go kind of like that angle to 120, just to kind of show the trigonal planar. But I could also have put the double bond over here. Notice I'm not moving the oxygens, I'm just moving where the double bond is. So I got three possibilities of legitimate Lewis dot structures. Up until this point I just said, hey, pick one, it doesn't matter which one. But the reality is all three are possible. This is what we're going to call resonance, and it occurs when there are two or more equivalent Lewis structures possible. And there's two or more. In this case, there's three. So what's happening in this case? What's really going on? Well, the reality is that we're having a multiple overlap. Okay, so we know the shape of this is going to be what shape? AX3, trigonal planar. Okay, at some point we're going to memorize that. Probably just not today, right? Trigonal planar. Okay, so planar meaning it's flat. So this is a flat molecule. And each one of the four atoms has a p orbital perpendicular to that plane. Now the p orbital will have a bottom part to it as well, but the model doesn't allow for that. Okay? So we have this p orbital. Now what we've been saying up until this point is just the two purple ones are overlapping side to side to form that pi bond. when you have resonance structures, which happens a lot with oxygen because of the p orbitals, the flat shape, and just the way it likes to form bonds, okay, is that here now, not only are these two p orbitals going to overlap, but these two and these two, we're going to get this whole cloud of delocalized electrons that can go anywhere. So two from here, one from here, one from here, a total of 6 electrons that are going to be just kind of hovering above and below the flat molecule, those pi electrons, okay? And so when the electrons get delocalized due to a multiple overlap of p orbitals, we call that resonance. Now, if I say my voice resonates down the hall, what do you imagine? Echo, because it's bouncing off the walls, resonating, bouncing back and forth. It's kind of what the word resonance means, okay? Sorry. The double bond is not flipping from here to here to here. The actual molecule is a hybrid of all 3 of these, okay? To where the double bond is equally shared among all. Now when we talk about it, let me just do this. Results from a multiple overlap of p orbitals okay? The electrons get delocalized and form a cloud above and below the molecule. So we have this thing called bond order. Bond order is just bond strength, okay? Stay with me on this because it's a little complicated. So the bond order for a single bond is 1. The bond order for a double bond is 2. The bond order for a triple bond is 3. Okay? Do I need to go over that again? All right. So bond order just tells the bond strength. Now, in an ordinary single, double, triple bond, that's not an issue. But in a case like this, the double bond is, now you're not ever allowed to draw the Lewis structure this way. But the reality is that the double bond is kind of shared by all. Okay? So the double bonds kind of split 3 ways. So they all have this sigma bond. So they all get a bond order of 1, plus they get 1/3 of the double bond each. So we would say the bond order for here is 1 1/3. It's going to be strong. All 3 bonds are going to be identical. Let me put all that. All bonds are identical. All bonds with the oxygen are identical. Stronger than a single bond, weaker than a double bond. But because the electrons get delocalized, it does add stability to the molecule. Okay? Bond order. The strength of the bond. Okay? Single. You got 1. I don't think I really need to write this, but double is 2. Bond order triple is 3. So in this case, the bond order is going to be what? What we just said. What for each one of these, they're all the same. What's the bond order between the sulfur and the oxygen is going to be? 1 1/3. Or 4/3. You have 4 bonds in 3 places, so it's going to be 4/3. Resonance generally occurs when you have multiple oxygens and there's at least 1 double bond. Obviously, you got to have pi bonds in order to have resonance. Okay, it's a multiple overlap. So, if I look at another one, I don't want to go to that one next. Let's go to NO3 minus. Well, let's do NO2 minus. Okay? NO2 minus. I have 5 plus 12 plus 1 is 18 electrons. Nitrogen, oxygen, oxygen, 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. Nitrogen is still electron efficient, right? So I got to do what? With which oxygen? Either one, right? So if you have this, we would draw it like this, and then we use a double arrow to imply resonance, or we could draw it like this. Again, I do not change the position of the oxygens, I'm only changing the location of the double bond. Okay? So if I can have choices on which one to form the double bond on, that's going to tell me I'm going to have resonance possibilities. So, brackets. What's the bond order going to be here?
1.5.
Okay, say it again, Adlai.
1.5.
1 1/2, 1.5. How did you know that?
There are 3 bonds and 2 bonds.
Okay, 3 bonds in 2 places, or we can see that the double bond is being shared between 2 places, so they each get a half. You always have 1 for the sigma bonds, plus whatever part of the double bond it gets. Are you with me on this?
Yes.
Now again, what's going to happen? This is AX2E. So that means it's a bent molecule, but it's still going to be flat. So the nitrogen's going to have a p orbital, and each oxygen's going to have a p orbital perpendicular to that plane. All of those are going to overlap. So we're going to have an overlap of 3 p orbitals. The electrons can go anywhere in that, but it forms this molecular orbital, this cloud of electrons above it, and since p orbitals have a top and a bottom, it'll be a cloud of electrons below it. How do the electrons get from the bottom to the top? We don't know. Just math says that there's a possibility, a probability they'll be there. Okay? Now, what if I just change this, and I have the joys of just being able to erase it, and I put another oxygen right here. Now, when I go to form my double bond, okay, so this is what we start with. Now when I go to form my double bond, how many choices do I have? 3. Well, I got 3 choices, right? So I can go the double bond here like we just did. We can go the double bond here like we just did. Or we can go the double bond here. So what would the bond order now be? It's going to be 1 1/3. So you have to pay attention to when the directions say draw the Lewis structure or structures for the following molecule. He's going to notice there's oxygen in all of these. Okay? Another one that we did oh, quit yawning. This is darn exciting. You guys, your brains are just tired from trying to soak all this in. We did SCN minus. Okay? I think it's minus. I'll tell you in a second. So we have 6, plus 4, plus 5, plus 1, so we get 15, 16 electrons. Carbon is my central atom with a nitrogen and a sulfur. 2, 4, 6, 8, 10, 12, 14, 16 electrons. So the carbon is electron deficient, okay? So when I go now, I can have two choices. I can take an electron here, because sulfur is in that oxygen family, it can form double bonds. Nitrogen can form double bonds. And we get SCN minus. But what else could I have done?
Triple bond.
I could have gone S carbon triple bonded to nitrogen. Because nitrogen can form that triple bond. Since I had two options, this is a resonance structure. Okay, now bond angles get a little tricky on this. What's the bond angle between sulfur, bond order, not angle, bond order, between sulfur and carbon in the double bond?
1.
Okay? Well, it's between here and here, right? So it's going to be 1 and 1/2. Because the double bond is going between a single and a double. But what about the carbon to nitrogen bond order? 5 over how many places?
2.
2.
5.
Which is what?
2.5.
2 1/2. Okay, it's between a double and a triple bond. And it's only got two possibilities, and so it's 2.5. Stronger than a double bond, weaker than a triple bond. Now, this is where we get to formal charge, and we did this as an example of formal charge. And so, in this one, the -1 formal charge, this was 0 and 0. In this one, formal charge turns out like this, when you calculate the formal charge for all of them. Which one is going to be the more, quote, dominant or the more favored structure? Okay, Reagan, why this one?
Something to do with nitrogen, like being,
Somebody help him, anybody know, Eddie? Nitrogen's more electronegative than the sulfur, therefore you want the negative charge on the more electronegative one. Okay? So if you have to pick based on formal charge, it's based on you want the minus charge to be on the more electronegative element. Yes, sir?
Oh, so sulfur couldn't form the triple bond?
No.
Because it's in the oxygen.
Right. Doubles, singles and doubles. Okay, let me just do one more that's a little bit more complicated but very common. Oh, let me come back to this one. What if I say HNO3? Well, let's go HNO2. HNO2. So now I have nitrogen, but where is the oxygen going to go? Okay? The hydrogen's going to go on one of the oxygens, right? So, we still have 18, what are we going to have? We're going to have 1 plus 5 plus 12, so we're going to have 18 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. So now, the nitrogen is still electron deficient, right? Hey, turn that just a hair towards you. The nitrogen is still electron deficient.
Yeah.
Right? So I need to form a double bond. Where do I form the double bond with? The top one, right? I'm not going to have an option to form it on this one. So is there resonance possible? No resonance possible because we only have just one possible Lewis structure. So the presence of the hydrogen removes the possibility of resonance. No, but in this case, what, Warren?
Why can't you form a double bond with that oxygen?
Because then it would have 3 bonds and oxygen's only going to form 2. Okay? Once it has its field octet, it's going to be stable, it's not going to want to bond anymore. Okay? back and listen to these videos, I realize I say the word okay about 20,000 times a day. I'm gonna really start working on not saying that. That's my kind of in-between thought comment. I need you just to be quiet. Last one. Have any of y'all ever heard of benzene or a benzene ring?
Yes, once.
C6H6. Benzene. When we do this, it turns into a 6-membered ring. Oh, did too many. That's right. Double bond here, single bond here, double bond here, single bond. Okay? So that's what it looks like. Alternating double bonds between the carbons, and it's in a ring, a benzene ring. But we just as easily could have put it like this. Where the double bonds were on the other spots. So what around each carbon, what's the AX formula? AX3, right? Which the shape's going to be trigonal planar. So it's going to be trigonal planar here, but it's going to be trigonal planar here, trigonal planar there, trigonal planar here, here, and here.
Okay.
The whole thing, the whole molecule is planar. Okay, so we got 6 carbons in a ring, but they're all planar. The hydrogens are all coming out on that same plane. Now, each carbon is going to have a p orbital with 1 electron in it. And all 6 of the p orbitals are going to overlap. Okay, so you have this big cloud of pi electrons above and below. They get delocalized, so those electrons can go anywhere to any of the 6 carbons. They're not localized there. They're just going to be moving and be repelling each other, but they're just no longer held right to this carbon any longer. So a lot of times they will draw this. This is what's called a Kekuli structure. Okay? And they'll just put the circle in the middle. That's kind of showing the resonance of that double bond. That is equally shared between all the carbons. And you assume, when you do a structure like this, you assume there's a carbon at each vertex. And then you always add hydrogens to fill the valences. In other words, make carbon have 4 bonds. But this is like, this shows my resonance. So what would the bond order then be between each carbon and carbon? Yeah, I heard that. What did you guys say over here? 1.5. Because it's like this double bond is back and forth here, this double bond's being shared back and forth here, this double bond's being shared back and forth. There are 9 bonds in 6 places. So it's 1.5 is the bond order. Okay, so we need to be able to be aware of resonance structures and the possibility of resonance. When you draw a Lewis structure, okay, all right, I wish I could pause the video because I want to talk about something else, but I can't yet. All right, that's resonance. Let's see if we can finish the chapter. If we don't finish today, we'll finish tomorrow for sure and start in on practice tomorrow. Tomorrow's going to be predominantly a work day.
Nice.
Just doing practice, AP, see what you really have to know on AP level for these type of questions. Okay? properties, and now we need to probably turn it now here and see. Properties of covalent substances. We've talked about properties of ionic. We've talked about properties of metallic and explained why they have the characteristics that they do. Okay? So we're going to go first, covalent network. Substances. What are my covalent network things? Which substances form covalent network? We've talked about this 1 or 2 times in the past. I'll give you a hint, there's only 5 of them. Carbon in what forms? So you get diamonds and graphite, which are both pure carbon. Okay? What else? That's 2 of them.
Silicon.
Just silicon because it's in the same family as carbon. It's going to bond the same way carbon does. Therefore, what's another one? I didn't hear. I just heard a mumble. Silicon carbide, SiC. It's a real sick molecule. Wakey wakey on a Monday. All right, and then the last one, sand, which is
SiO2.
SiO2. So, if it's not one of these, okay, it's not covalent network. These are the only ones you have to know for covalent network. Now, you have to just memorize that. Okay? So what are some of the characteristics that we know about a diamond? What about its melting point? High melting points. Okay? So, very high melting points. Is there a molecule of a diamond? Just this huge crystal. So covalent network is just this non-metal bonded to non-covalently bonded to non-metal, covalently bonded, covalently bonded, covalently bonded. Okay? But it just forms these huge crystals instead of an individual molecule. Forms crystals, not molecules. Is everybody following me on that one? Now, graphite is unique. Okay, most don't conduct electricity because why won't they conduct? What is electricity? Are there any charged particles in a diamond? No, the covalent bond, the electrons are shared, there's no charges. So plus each atom is held rigidly in the crystal lattice structure, so you don't have any movement either. So kind of there's nothing to conduct electricity. But graphite, there we go. How many carbons is each other carbon attached to? 3, right? So the shape's going to be trigonoplanar. Graphite forms these layers. And the layer each has a p orbital perpendicular to it. So all the white are the p orbitals putting the layers together. So you get this layer of carbon, then this cloud of delocalized pi electrons in between, another layer of carbon, and then a layer, and then more pi electrons, and another layer of carbon. So when you're writing with your pencil, you're actually getting the layers just wiped off each other. Bonded very strongly in 2 dimensions, but the layers are very weakly bonded, which is why this model allows for the motion. Very weakly bonded to one another. Fix one, I broke the other one. Okay? So it just moves. So when you're writing with your pencil, you're just doing layers off of one another. Graphite is a great lubricant because the layers slide so readily over. I don't know if any of y'all ever did the box, soak the box derbies, whatever, you know, with the Boy Scouts where you have the cars. You're not allowed to use a liquid lubricant on the wheels. You have to have it dry. So everybody uses graphite powder because it's a great lubricant because the layers slide over one another so easily. But in addition, because it has these pi electrons between the layers that are delocalized, you have charged particles that can flow. So graphite does indeed conduct electricity. And I told you the story about the student that stuck the pencil lead back in the socket, just kind of proved that point. Okay? So most don't conduct electricity, but there's an exception, which is graphite. And it's due to the delocalized pi electrons between the layers. Okay? They're also going to be very hard. Diamonds are the hardest natural substance. Silicon carbide is used in industrial sandpapers. Okay? They're just bonded strongly in 3 dimensions and held together. Okay? The one thing that you might want to know about this is that this is 3D, this is only 2D. You know what I'm saying? This is bonded strongly in all 3 directions. This is bonded strongly on the X, Y, but the layers are weakly bonded. Okay, so this is strong 2 dimensions, but this is strong in 3. So a 3-dimensional covalent is going to be much stronger. Okay, that's covalent network. All you pretty much need to know. Covalent molecular. Now, covalent molecular are going to be broken into 2 different categories: nonpolar and polar. What's the only type of attractive force between nonpolar molecules? Okay? Contain only weak LDFs. Okay? So what does that mean then about their melting and boiling points?
Low.
Very low melting and boiling points. So what state do you think most of these are in? There's going to be liquids or a gas, okay? Most are gases or volatile liquids. Now you probably need to define the word volatile. What does the word volatile mean? Stay with me, Quinn.
Bubbly.
Unstable.
Okay? Unstable is what we think. We think of this as being explosive. That's not really what it means. But we're close.
It evaporates quickly.
It evaporates quickly. What would that mean about its vapor pressure? High. You're going to have a lot of vapor above the liquid because it's evaporating quickly. So it's going to have a high vapor pressure. That's just a flashback, but you might as well write it down. We might have to, there we have it. Okay? High vapor pressure. What do LDFs vary with? How do they get stronger?
The size of the electron cloud increases.
The size of the electron cloud, right? So bigger molecules are going to tend to be your liquids. Your smaller nonpolar molecules are going to be gases. Think about it. Hydrogen, H2. You almost have to get a near absolute 0 to make it stick together. Helium, the boiling point is 4 Kelvin. Okay? So, I mean, very, very weak LDFs. Oxygen gas that's in the room right here. O2, it's a nonpolar molecule. Nitrogen gas that's in the room right now. It's a nonpolar gas. Neon gas. Fluorine is going to be a gas, F2, Cl2. But Br2 is going to be a liquid. Because now the molecules are a little bit, the electron cloud's bigger, LDFs get a little bit stronger, but it's still going to evaporate very quickly and easily. Okay? So, when we talk about hydrocarbons, CH4, C2H6, C3H8, C4H10, C5H12, C6H14, C7H18, H16, C8, H18, and we just continue to go up the chain. These four are all gases at room temperature. This is your octane gasoline. These are all volatile liquids. Due to the increased LDFs. I mean, hey, you have to admit that it's pretty awesome to be able to understand that when I'm talking about all this complicated stuff, LDFs and why it's a liquid and the vapor pressure, and you guys are understanding, well, mostly, okay? You're working towards understanding all the, I mean, you're figuring out why the world around us, why, now we know why oxygen's a gas and water is not, okay? So, non-polar, very low melting, gases or volatile liquids have very weak LDFs, but they do vary with the molar mass. A lot of the size of the electron cloud. Okay, now you definitely need to move it over here. Okay, so now we're going to go to polar molecules. What do they have? What IMFs?
Hydrogen. Dipole, dipole.
They have LDFs, dipole-dipole, and possibly, not all do, possibly hydrogen bonds. So generally speaking, what does that mean about the IMFs? Stronger. Still, gases, gas or liquid at room temperature. But generally, and that's a word, generally have higher melting and boiling points than non-polar molecules. Now what do we think about the conduction of electricity for both polar and non-polar? Are there charged particles? Are molecules charged? No. So neither conduct electricity. Okay? Neither, they're all brittle. Think about ice. You hit ice, it shatters into smaller pieces. Okay? So they're brittle. Okay? So we have the characteristics, and we understand this all about the strength of the attractive force. So, to summarize this, we have this wonderful chart. This is the chapter in review as far as properties. This is yours to keep. Are we passing it down? All right, now listen. So this kind of tells you everything that we were just talking about. Okay? We can explain the properties of ionic. Okay? The electrostatic attraction or the Coulombic attraction is what holds ions together. It's the metallic bond that holds metals together. Covalent network, it's non-metals covalently bonded in huge crystals. Okay? Non-polar and polar. Okay? We're talking about the forces that hold them together. London forces only. But for polar, you're going to have possibly hydrogen bonds. Okay? So we need to be able to understand the properties based upon what type of molecule it is. We need to be able to recognize what type of substance it is, and we need to be able to then identify the properties based upon the type of bonding, the type of forces holding them together. That's explaining the world around us. That's explaining why things do what they do. Okay? This is kind of starting to put almost everything that we've learned together now that makes sense. Y'all have a wonderful day.
I will try my best.